4.5 is about the area between curves. So to do this, let's first look at just a basic sketch and talk about what curves might look like. So let's say we have some function y equals f of x and another function y equals g of x, and we're going to find the area on some interval from a to b. So really the only difference here, if I erased g of x and we were finding the area between a and b, or on the interval from a to b, of y equals f of x, we would be talking about the area all the way from that curve down to the axes. So if that was all the way shaded in, if we were looking at this whole area, and if we did that, that would be the integral from a to b of f of x dx. That is what we just worked through in much of this unit. The area would be the integral from a to b of f of x dx. And then if we wanted the area from g of x down, I'm going to use blue here, that would be, if we're talking about this area over the same integral, that would be the integral from a to b of g of x dx. Now, if we're looking for the area in between them, if we're looking for just this red area, logically it should make sense that what we really need to do to find this red area is we need to take the integral from a to b of f of x dx, and we need to subtract the integral from a to b of g of x dx, because I have this top area, f of x, going down, the green area, and then we're double counting this blue piece if we find the area of g of x. So what I want to do is I want to remove that area, that g of x area. So it should make sense that what we can do is take the top area, f of x, and subtract out the bottom area, g of x, and that would in fact give me the red area that I'm looking for. And we know from our integration properties that we could actually combine this, the integral from a to b, we could actually put f of x and g of x together inside one integral. So this intuitively makes sense when we have two functions that are both above the x-axis. We're talking about positive areas. But what you should be questioning almost immediately is, well, what happens if one or both of the functions are below the x-axis? So let's kind of analyze those cases as well. So let's look at two different curves. I'm still going to refer them as f of x and g of x, but let's look at what's happening on the interval from c to d if we're actually, part of that area is going to be negative for at least one of the functions. So let's think about this. If we're asking for this area here, we would be looking at the integral from c to d of f of x. That would give me this top piece, which would be positive area. And if you're thinking about this area down here, this is going to be negative area. So we could represent that area as the integral from c to d of g of x dx. I better make sure I have a dx here. And we're looking for these the total area here, which means in theory we should be adding them together. But remember, g of x is negative. It's going to be a negative area. So we can either think about that inside as negative or think about it as putting a negative in between them. So again, the integral from c to d of f of x minus g of x dx. So now we have looked at the case where they're both positive, where one's positive and one's negative. So the last case we should really be thinking about is what happens if they're both negative, and that case should follow pretty intuitively as well, but let's look at it anyways. So let's look at the integral from h, or let's look at the area between h and k, so I just added an h and a k, between those two curves. And let's think about, well, if I found the integral from h to k of g of x dx, that would actually be the whole area between the x-axis and g of x. And since this is below the x-axis, this would give us a negative area. And if we look at the integral, I'm going to erase this f of x, let's move it over here. If we look at the integral from h to k of f of x dx, we would be looking at the area between f of x and the curve. So if we follow that same logic that we're subtracting these two things because of what we had started with at the beginning of this, f of x minus g of x inside, this area is going to be negative. Then we're going to be subtracting a negative area, which means we're going to be adding, which means we would in fact just get this purple area that we wanted to get to begin with. So no matter the case, both positive, both negative, one of each, we are still going to come to the conclusion that to find this area, we can subtract one function from the other over the integral that we're looking at. So then now that we've analyzed all the different cases, let's just kind of summarize this in one place. The key thing when you're finding the area between two curves is that you need to identify the bigger curve or the higher curve, or depending on what you're looking at, the more to the right curve if we're looking at curves that are being formed with the y-axis or functions in terms of y. You need to identify the big curve versus the little curve because you need to be subtracting the area of the bigger curve from the smaller curve. So in the example that we just looked at, f of x was the function that was on top. That was the bigger curve. So the area over some integral from a to b, or over some interval from a to b, is the integral from a to b of the big area minus, or the big function minus the small function. That works similarly. So this is if we're talking about, we're looking at the area with the x-axis. This is if we're talking about looking at the area with the y-axis. So just pay attention to what we are integrating with respect to. So what we're going to do for the rest of these notes is we're going to look at 7 different examples where we have two curves and we're finding the area between those two curves. So oftentimes you're going to have to sketch graphs of these on your own in order to determine which curve is above and which curve is below. Oftentimes you're going to have to find the intersections by hand, but just for time's sake for these notes, I actually put each of the graphs in here so that we can just look at what's already there and identify the big and small functions. So this first example, remember anytime you see this little symbol, that's me indicating to you that we can use a calculator there. So the directions say, find the area between the two curves. You must show the integral setup even if you're using a calculator, just like you would have to do on the AP test, you need to show the setup. Sketch the graph of the functions as well. You can use your calculator to evaluate and find the intersections. So here we have two areas actually. If you look at these two curves, it looks like there are two areas between these two curves. Let's use different colors. So there's this area on the left and there's the area on the right, which means the first thing we need to do always is find the intersections. To do that, we're going to set the functions equal to each other. And then since this is a calculator problem, there's a couple ways you could do this on your calculator. You could graph the functions and find where they intersect. You could use equation solver or use the solver function on your graphing calculator. Here we have the graph to help us since I already did that on Desmos. This is going to give us that our intersections are 0, negative 1.699, and 3.699. By looking at the graph, we can see that we're going to have multiple integrals, 2, that we're going to have to set up because there's 2 different areas. So let's talk about this one first. So for the first, the green area, I'm going to take the integral from negative 1.699 to 0 of, and I'm looking at that area between the two curves. So I am going to take x squared plus 2 pi x, and I'm going to subtract the other function, x cubed minus x squared. So I'm looking at which, it honestly doesn't matter which one you're subtracting here, but I'm looking at the blue curve is the bigger one in terms of forming an area with the x-axis. The reason it really doesn't matter is because if you compute this integral on a calculator, as I have set it up here, you get negative 3.715. And since we're talking about the area between curves, even though this area is below the x-axis, we're talking about how much total area is trapped between them, so you're going to think about it as a positive area anyways, because we're saying how much total area is between them. So for this particular one, it actually really doesn't matter which one comes first and which one comes second. So this is going to give you negative 3.715, and I'm just going to write that as 3.715 positive because we're talking about combined area. Then we're going to set up the right hand, or the second area, which is going to be the integral from 0 to positive 3.699. And because I'm running out of room, I'm just going to set it up this way. I'm going to say of g of x minus f of x. You are more than welcome, as long as those are the functions that are defined in the problem, to set it up that way on tests, on the AP test as well. That area is going to give you 29.923. I'm out of space. So the total area between those two curves is going to be 33.638. So again, even though the green area is negative, the question isn't asking us how much area is above or below. It's asking between the two curves, what's the total amount of area? And the total amount of area means both of those areas should be positive. Let's go ahead and look at number 2. Find the area between the graphs y equals cosine of x, y equals sine of x. And know that even though I gave you these graphs, I could give you this question without giving you the graphs. You should be able to sketch cosine of x and sine of x and figure out where they are intersecting without a calculator. Notice this one does not have a calculator symbol at the beginning. The area that we're talking about here, again, I am giving you these graphs just to save us time on these notes. I don't think you need to see me graph functions. So I see that first I need to find my intersections, which here is going to be pi over 4 and 5 pi over 4. And there's only, it specifically says between one region. So this is the only area I'm looking at, which means there's only going to be one integral. The red graph, which is sine of x, is clearly the graph that is on top of the two. So the red graph is going to be the first one inside my integral. So I'm going to have sine of x minus, I'm going to set up the integral part afterwards. The blue graph is my cosine graph, which is underneath cosine of x. And we're going to be integrating from pi over 4 to 5 pi over 4. And this is all with respect to dx. Now this one doesn't have the calculator button. You should be able to integrate this by hand. Sine goes to negative cosine of x. Minus cosine of x goes to sine of x, and we're evaluating this from pi over 4 to 5 pi over 4. And for time's sake, I'm going to save us some work here and just tell you that that is 2 root 2, but you should be able to evaluate that completely by hand. You should be able to do number 2 start to finish completely by hand, including sketching the functions. All right, go ahead and pause the video and see if you can set up the integral and find the intersections for number 3. Something I want to point out is that you are now looking at functions in terms of y, which means when you integrate, you're going to be integrating with respect to y. So keep that in mind when you are setting up your integral. So again, when you're working through these problems, if there was no graph, step 1, sketch a graph. Step 2, find the intersections, which means that you're setting the functions equal to each other. So 3 minus y squared equals y plus 1. This is just a quadratic. Y squared plus y minus 2 equals 0. It's actually a nice quadratic that factors. It's going to give you negative 2 and 1 as your solutions. So sketch a graph, figure out the big and little functions, find the intersections, and then set up your integral and integrate. So this is going to be the integral from negative 2 to 1. Of, what do we say our big one was? 3 minus y squared minus the small function y plus 1, all being integrated with respect to y. Now, if this was a calculator problem, even though there's y's in here, you could still type it in as x on your calculator because the integration process is the same. You're going to get the exact same value. If you were doing this by hand, what you should do is simplify this. That's going to give you negative y squared minus y plus 2, so that you can then integrate using the power rule. Negative y to the third over 3 minus y squared over 2 plus 2y, being evaluated from negative 2 to 1. And for time's sake, I'm just going to tell you that this ends up being 4.5. So there are 4 more problems to work through. My recommendation is that you pause the video and you work through a problem and then you skip ahead and see how you're doing. If you need to follow me as we go, that's fine as well. All right, so the very first thing I'm going to do is find the intersections. And again, it's good, especially when you're practicing, to pretend like the graph's not there and you can't just see the intersections from the graph. The graph I added on to sort of save us a little bit of time. So you can see this from the graph as well, but this is pretty basic algebra here, solving for x. You're going to get that x is 0 and plus or minus 2. We have 3 points of intersection, which makes sense because we have 2 areas of interest here. We have this area in blue and the purple area. So let's talk about the blue area first. In terms of the blue area, the bigger function is the one that you can see on the graph in red, which is the 3x cubed minus x squared minus 10x, which means that the other function is going to be our smaller function. So let's go ahead and set up that integral. If you work through this, you can simplify that integral. It's going to end up simplifying to be 3x cubed minus 12x, which makes sense. You can get that from right here. So since I'm out of space, I'm going to go up top. The integral from -2 to 0 of 3x cubed minus 12x dx. We can integrate that using the power rule. That's going to give us 3x to the 4th over 4 minus 12x squared over 2, which is just going to be 6x squared. And we're evaluating that from -2 to 0. And when we evaluate that, we're going to get 12 for our blue area. Now let's go ahead and find the purple area. The purple area is going to be the integral from 0 to +2 of the big function, or the function on top, which is the green function, which is the quadratic, -x squared plus 2x, minus the other function, 3x cubed minus x squared minus 10x, all integrating with respect to dx. I'm going to distribute and combine like terms so that I can actually do that integration by hand. That's going to get me here, and then if I integrate -3x to the 4th over 4 plus 6x squared from 0 to +2, and that is going to give me also 12. So our total combined area under both curves is going to be 24. If I had more room, I probably should have set this up so that the whole integral went out like I did on my handwritten notes, but area under the curve is going to be 24. For number 5, the directions probably should have said just look at the first, or just look at one intersection, because these graphs are going to continue to intersect. However, I'm telling you that now, so we're going to look at this intersecting area. Again, if you were not given the graph, you should be finding those intersections first, so setting the functions equal to each other and solving. This is going to be true when x is equal to 0 or 1. The red area, the sine function, is obviously the bigger function, and the green one on the bottom is the smaller function. So we can set up our integral, our one integral, from 0 to 1 of x squared, of sine of pi x minus x squared minus x, all being integrated with respect to x. This is another integration that you could do by hand. This is going to be -1 over pi times cosine of pi x minus x to the 3rd over 3 plus x squared over 2, and we're integrating from 0 to 1. This is going to give you 2 over pi plus 1/6, which you would obviously be allowed to leave like that. If you wanted to convert it to a decimal, that would be 0.803. And know that obviously you need to give yourself a little bit more time to actually do the work of plugging in 0 and 1 and getting to these answers. I'm rushing through them because evaluating, plugging in numbers is really not the calculus part of these problems. So it's fine to pause the video, work through it, make sure you're getting the same answers as me, because we all know I am very human and make mistakes all the time. Let's look at the last 2 problems. All right, notice for both 6 and 7, the little my version of a calculator symbol is on there, which means you would be finding the intersection on a calculator, you would be evaluating the integral on a calculator. So the only work that needs to be seen here is the setup of the integral. I wouldn't even necessarily need to see how you found the intersections because you're doing that on a calculator. I would expect to see that you did find the intersections. So I would probably expect to see somewhere even if you didn't show all of this, I'll show you what I would expect to see. I want to know where these two things are equal. And then you could even say on calculator, x equals -5/2 plus or minus the square root of 5/2, which I'm not even going to take the time to simplify, although you can see on the graph here what those intersections are. If you're given a graph, you could just circle the intersection values that we're talking about. So, big curve for this teeny tiny little area that we're talking about here. The big curve is going to be f of x. The small curve is going to be g of x. I'm going to say the integral from -5/2 minus root 5/2 to -5/2 plus root 5/2. And you could write the functions out. On this one, I'm going to show you that you could also just write of f of x minus g of x dx. And you can do this because those functions are defined in the original problem. You could also have written 5/x plus x plus 5 because you're distributing that. So either of those is fine. And then this is coming from the calculator, so you're evaluating that integral on the calculator. That's going to give you 0.778. Now let's look at the last one. On the last one, we have multiple areas we're going to be talking about. We have an intersection here, and we have an intersection here. So the minimum I would expect to see is that at least you write intersections on calculator and you identify those x values for me. I don't need you to necessarily show f of x equals g of x, setting all of that up. So you could just write this. Intersections on calculator, x equals 0, 1.033, and 2. Those three intersections means that I'm going to have two separate integrals, one from 0 to 1.033, one from 1.033 to 2. I'm going to go ahead and use f of x and g of x again here. So for the red integral, the red curve is the big curve, and the red curve is g of x. So g of x minus f of x dx. For the other one, the green area, the opposite of true. So f of x is our big area, and g of x is our little area. And again, this is all completely on the calculator, and this is going to give you, and there should be a plus in between these two integrals, plus the first, let's put that in the right spot, plus, that is going to give you 2.114. So most important takeaways from this section of notes. You are finding the area between two curves, so you're going to set that up, big area, or bigger curve minus smaller curve. You're going to integrate that. To find the bounds of the integral, you're going to identify where those two curves intersect. Sometimes that's going to be in more than two places, which means you will have more than two integrals. Remember that if you're not given a graph, sketching a graph will help you identify how to set up your intervals and help you identify the intersection points. Looking forward to working with you more on this in class. See you then.